Hi guys, I will explain the arbitrary rotation of coordinate system or cross-section from rotation of coordinate system and the Mohr circle to summary. Here I have a quiz for you. I minimum is the minimum second moment of area as shown in the Mohr circle. Which of the following rectangular shapes has the smallest I minimum? I explained all the contents from the first moment of area to how to draw the Mohr circle. In this video, I will explain the arbitrary rotation of coordinate system or cross-section. This figure explains the rotation of coordinate axis as shown in the last video, H43. Here, we have to remember that the equations was derived assuming that the coordinate system rotated clockwise from zy coordinate to z prime y prime coordinates. Therefore, the value of theta is positive when rotating in a clockwise direction and negative when rotating in a counterclockwise direction. Let's look at the clockwise rotation of the coordinate axis and how it appears on the Mohr circle. The blue thick lines represent the current axis, and the green thin lines represent the coordinate axis rotated clockwise by an angle theta. The sign of theta is plus because z component is plus and the y component also plus. If the coordinate system rotates by theta on the cross-section, it rotates by 2 theta, which is twice the rotation of the coordinate system in the Mohr circle. And the direction of rotation is the same. In the figure on the left, if the blue coordinate axis rotates clockwise by theta and becomes the green coordinate axis, the new coordinate system, z prime, y prime, coincides with the principal axis. In the Mohr circle, it rotates clockwise by 2 theta in the same direction to coincide with the principal axis, which is the horizontal axis. What if the coordinate system rotates counterclockwise by theta? Referring to the figure on the left, the coordinate values can be obtained as in the equation 3. If this is arranged as a matrix form, it becomes the equation 4. And comparing this result with the previous clockwise equation, it can be seen that it is the same as the result of substituting minus theta instead of theta. Therefore, it can be seen that theta has negative value when rotating in the clockwise, and it has negative value when rotating in a counterclockwise direction. Let's look at the counterclockwise rotation of the coordinate axis and how it appears on the Mohr circle. The blue thick lines represent the current axis, and the green thin line represent the coordinate axis rotated counterclockwise by an angle theta. The sign of theta is negative because the z component is positive and y component is negative. If the coordinate system rotates by theta on the cross-section, it rotates by 2 theta, which is twice the rotation of coordinate system in the Mohr circle. And the direction of rotation is the same. In the figure on the left, if the blue coordinate axis rotates counterclockwise by theta and becomes the green coordinate axis, the new coordinate system, z prime, y prime, coincides with the principal axis. In the Mohr circle, it rotates counterclockwise by 2 theta in the same direction to coincide with the principal axis, which is the horizontal axis. From now on, let's look at the case where the cross-section rotates rather than coordinate axis. The cross-section of original blue thick line rotated clockwise by theta to become that of green thin line. Let's see how it appears in Mohr circle. As with the rotation of the coordinate system, if an object rotates by theta, it rotates by 2 theta in the Mohr circle, but in the opposite direction. In the figure on the left, the cross-section with the blue line rotated in the clockwise by theta and became the new cross-section in the green color. In the Mohr circle, it rotates counterclockwise by 2 theta. This time, the cross-section of original blue thick line rotated counterclockwise by theta to become the cross-section of green thin line. Let's see how it appears in the Mohr circle. If an object rotates by theta, it rotates by 2 theta in the Mohr circle, but in the opposite direction. In the figure on the left, the cross-section with blue line rotated in the counterclockwise by theta and became the new cross-section in green line. In the Mohr circle, it rotates clockwise by 2 theta. How would it appear in the Mohr circle if the positive horizontal axis points to the right? In this case, the increasing direction of the second moment of area in the Mohr circle must also point to the right. In this way, the direction of rotation of the coordinate axis coincides with that of rotation on the Mohr circle. In the figure on the left, if the coordinate axis of the blue lines rotates in the clockwise by theta and become a new coordinate axis, x prime and y prime, in the green color, which coincide with the principal axis. In the Mohr circle, it rotates clockwise by 2 theta to coincide with the principal axis, which is horizontal axis. Now, let's look at the case of rotating in the opposite direction to the previous example. In the figure on the left, if the coordinate axis of blue lines in the counterclockwise by theta and become the green color coordinate x prime, y prime, which coincide with the principal axis. In the Mohr circle, it rotates counterclockwise by 2 theta to coincide with the principal axis, which is the horizontal axis. When the positive horizontal axis points to the left in the cross-section, and the increasing direction of second moment of area of a Mohr circle also points to the left, the axis rotation by angle theta in the actual cross-section means 2 theta in the Mohr circle, and the direction of rotation is the same. It must be remembered that, in this case, the cross-section does not rotate, but the coordinate axis rotates. When the cross-section rotates, their direction of rotation are opposite each other. When the positive horizontal axis points to the right in the real cross-section, and the increasing direction of second moment of area of the Mohr circle also points to the right, the axis rotation by angle theta in the actual cross-section means 2 theta in the Mohr circle, and the direction of rotation is the same. It must be remembered that, in this case, the cross-section does not rotate, but the coordinate axis rotates. when the cross-section rotates, their direction of rotations are opposite each other. The coordinate components of the small area dA with respect to z prime y prime axis can be expressed as the equation 1 in terms of zy axis components. Equation 1 can also be expressed in a matrix form, but in fact it is the same as the matrix equation to find the coordinate of each point when the coordinate system is rotated. Using the matrix equation 2, the relative equations can be derived to obtain the second and the product moment of area for the rotated coordinate axis. It is also possible to obtain the original coordinate zy from the rotated coordinates z prime y prime using the inverse matrix. Rotation of the cross-section by theta is equivalent to the rotation of the coordinate axis by theta in the opposite direction. Therefore, the expression obtained in the previous slide can be used as it is. Let's prove this. Let's assume that theta is positive. If the straight distance from origin to the small area is r, the coordinates before and after rotation can be expressed as equation 4. Therefore, if we arrange this, we can get the equation 5. We can express these equations in the matrix form of 6. It can be seen that this result is the same as the equation obtained in the previous slide. This result is expectable because in the previous example, the coordinate system rotates clockwise by theta, but in this example, the cross-section rotates counterclockwise by theta. The answer to the quiz is number 3. All the 3 cross-sections have the same height but different widths. Since number 3 has the smallest width, the minimum second moment of area with respect to y-axis has the smallest value among the 3 cross-sections. Here we have a summary. If the positive direction of the horizontal axis and the increasing direction of the second moment of area in the Mohr circle are aligned together, the rotation of the axis by the angle theta in the actual cross-section is equivalent to the rotation by 2 theta in the Mohr circle, and the directions of rotation are the same. When the cross-section does not rotate and the coordinate axis rotate, the direction of rotation is the same as in the Mohr circle. When the cross-section rotate and the coordinate axis do not rotate, the direction of rotation is opposite in the Mohr circle. Rotation of the cross-section by theta is equivalent to the rotation of the coordinate axis by theta in the opposite direction. If you watch the previous videos, you can easily understand upcoming videos. In the previous video, E45, I explained the method for proving the relationship between Mohr circle and the second and the product moments of area. Recently, I explained how to draw the Mohr circle step by step. The next video is Price Tier Part 20, Moment of Area Part 9. I will explain the characteristics of a Mohr circle and the Z channel, which is an actual application case. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you next video. Goodbye guys.